Because the raw data from a microarray experiment are the set of images, here's a brief summary of the computer representation of images. Consider an image or picture with a matrix or grid overlaid. The smallest element of an image is a pixel. For an m by n pixel image, each pixel has a location denoted by its x and y coordinates. Each pixel also has an associated intensity value, which is denoted by f of x and y. And the size of the pixel is given by the delta x and delta y. The rule of thumb for custom spotted arrays is that the pixel size is 1/10 of the size of a spot or probe. Here's an example where we have an m by n pixel image. Here, x and y coordinates have been labeled from 0 to m-1 and 0 to n-1. This is a monochromatic image, so the pixel intensities only take on a value of 0, representing black, and 1, representing white. So f of x and y is either 0 or 1 for each pixel in this grid. We can see the intensity values for specific coordinates. When x equals 0 and y equals 0, f of x and y equals 1. When x equals 11 and y equals 14, f of x and y equals 0. When x equals 22 and y equals 9, f of x and y equals 1. When x equals 21 and y equals 10, f of x and y equals 0. F of x and y is usually a grayscaled value in a monochromatic image. Each f of x and y represents the brightness of the pixel at location x and y. The number of pixels used for scanning is called resolution and is usually specified by two numbers: the number of lines read and the number of values in each line. Pixel intensity values are stored as binary numbers. Binary numbers are sequences of zeros and ones. A binary digit, usually abbreviated bit, can hold one binary value, either 0 or 1. For a 1-bit digital image, the computer uses 1 bit to represent each pixel value. The pixel is either 0 for black or 1 for white. In a 2-bit digital image, the computer uses 2 bits to represent a pixel value. The pixel may be 0, 0, which is black, 1, 1, which is white, or one of two shades of gray. Our numbering system is denary, that is, the base or radix is 10. Therefore, numbers are naturally represented as multiples of ones, tens, hundreds, thousands, etc. When storing a number like 365 using our denary system, it looks like this. There are 5 ones, 6 tens, 3 hundreds. But if we were using a binary system, we use a sequence of binary digits, each having a value of 0 or 1. A sequence of 8 binary digits is called a byte. For example, using 8 bits, the number 87 would be represented using this sequence of zeros and ones. Note that the translation to 87 appears at the bottom of this figure. The number of bits used to store one pixel of an image is called the color depth. Letting n be the number of bits, there are 2 to the n possible binary sequences of length n. For example, a color depth of 1 indicates there are 2 to the 1, which equals 2, colors available, black and white. A color depth of 2 means there are 2 to the 2, which equals 4, colors available, black, white, and 2 grayscale values. Most images are stored using n bits. For example, an 8-bit or 1 byte image has 2 to the 8 possible values ranging from 0, representing black, to 2 to the 8 minus 1, which equals 255, which represents white, with 254 grayscale values. The radix is 2, so each number is represented as a linear combination of powers of 2. If the color depth is too small, different shades of gray will get mapped to the same value. Here are 3 images stored from left to right as 8-bit, 4-bit, and 2-bit images.